Hi everybody, welcome back to the Feynman technique. Today we're going to be evaluating the Basel problem, that is the sum of the reciprocals of the squares. I know I've done that problem on the channel before, but that was kind of the standard proof of the Basel problem. This one's going to be a little bit different. We're going to be using a combination of um, complex numbers and Feynman's technique. So let's get started. First step is just to state this. This might seem like an odd first step, but we're just going to state that this is true. And of course it is. Anybody watching this channel is more than capable of making that leap. And then we'll make the substitution u is equal to x over t. And we get this. So we perform that substitution. This splits into this. And of course, this integral right here is pi over 2. So we just end up with this, which means, oh, and then to further evaluate this, what we're going to do is state this. All we did was split this integral up into two separate integrals using the, I forget what that property is called, but you can do that. The integral from 0 to infinity is just the integral from 0 to 1 plus the integral from 1 to infinity. And then we perform the substitution. U is equal to 1 over x, and we get this. We get that the integral from 0 to infinity of natural log x over x squared plus 1 is just this, plus, and we perform the substitution on this one. So we're performing the substitution on this one. That gives you this, and then that simplifies to this. And we have something minus the exact same something, and that's equal to 0. So we just showed that the integral from 0 to infinity of natural log x over x squared plus 1 dx is equal to 0, meaning this entire term is going to drop out. And then, finally, we have this. Don't forget, this is what we started with. All the way up here, all this work was done just to show that this is equal to this. All right, so now that we have that, let's continue. Let's let our t squared equal -1. So that implies that our t is equal to plus or minus I. And it doesn't matter which version we choose, we end up getting the same thing. So if we choose t is equal to I, the evaluation looks like this. Of course, plugging in t is equal to I squared is going to give you -1. So we'll end up with this integral being equal to pi over 2 times the natural log of I over I. I is, of course, well, the principal value of I, which we are going to be using, is e to the I pi over 2. Using the properties of logarithms, that just becomes I pi over 2, and that all simplifies to pi squared over 4. So we've shown that this integral is equal to pi squared over 4. And you get the same thing whether if you plug in -I. And I just wanted to show that. It's the same process, and you still end up with pi squared over 4. All right, so now we've shown that the integral from 0 to infinity of natural log x over x squared minus 1 is equal to pi squared over 4. That's that's a little bit related to the answer to the Basel problem. Let's see where this goes. All right, so I just restated that. That integral is equal to pi squared over 4. And then let's just state this. The integral from 0 to infinity of natural log x over x squared minus 1 is equal to 2 times the same integral except going from 0 to 1. And I'm not going to show how you show that. Anybody watching this channel, well, basically, you do the same thing we did before. You split this up into two separate integrals, one going from 0 to 1, the other going from 1 to infinity, and then perform the substitution u is equal to 1 over x, and you'll just get this. Okay. All right, so now let's let some function g of t be equal to the integral from 0 to 1 of x to the t minus 1 over x squared minus 1. Now, originally, when I was first doing this, I did not have this minus 1 here. But I knew that would get me yelled at in the comments if I did that. Because the integral from 0 to 1 of x to the t over x squared minus 1 dx doesn't converge. So I added this little -1 here. And now this does converge. This will converge for, I believe, um, for certain values of t. Okay. So this one at least works. So there's our g of t. So next, let's take g prime of t using the Leibniz rule for differentiation under the integral sign. So g prime of t is the derivative with respect to t of this function of t. Using the Leibniz rule, we just bring that derivative inside the integral and then evaluate the partial with respect to t of the integrand, and this is what we get. All right, and now we'll notice that if we take 2 times g prime of 0, we get 2 integral 0 to 1 of natural log x over x squared minus 1 dx, and that is equal to pi squared over 4, which we showed previously. Okay, so from here, let's just state this. 1 over x squared minus 1 is equal to negative sum as n goes from 0 to infinity of x to the 2n. All right. And that's of course good for the absolute value of x greater than 1. Or less than 1, I'm sorry. All right, so now we have g of t, which was well, we can plug in this sum for this expression right here, giving us g of t is equal to this times this sum. And I used the negative attached to it just to switch the order of x to the t and that -1. So g of t is equal to this. And then switching the integration and summation notations there and splitting this up into and just basically distributing this x to the 2n inside of there, we end up with this. And then evaluating the integral, we end up with this. So there's a sum representation of our g of t. So now let's take g prime of t just by differentiating this sum term by term with respect to t. Of course, this with respect to t is just going to give us 0 because it's constant. And if you take the derivative with respect to t of this, you'll just end up with this. So now we have g prime of t is equal to this sum right here. Okay, but we know that 2g prime of 0 is equal to pi squared over 4, right? But that's also equal to this. All we do is take this and plug in t is equal to 0. So 2 of this is equal to pi squared over 4, which implies that just 1 of this is equal to pi squared over 8. And of course, that sum right there, if you take the first 4 terms, you'll see that this sum right here is just 1 plus 1 over 9 plus 1 over 25 plus 1 over 49, so on and on and on and on forever. And we know that that is equal to pi squared over 8. So now let's set j equal to the sum that we originally wanted to find out. We want to know what this is equal to. So we set some constant j equal to it. Okay. Now let's take j and subtract pi squared over 8. But subtracting pi squared over 8 is the same thing as subtracting this thing right here. So if we take this and subtract this, you'll notice that this will drop out, this will drop out, this will drop out, and you'll just be left with 1/4 plus 1/16 plus 1/36, 1/64, on and on and on and on forever and ever. And you could continue the pattern yourself if you would like to. And then you can factor out a 1/4 from that, and you'll be left with 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. And that is exactly j. So we've shown that j minus pi squared over 8 is equal to 1/4 of j. And we're pretty much done. So now we have 3/4 j. If we do the algebra there, we subtract 1/4 j from both sides, giving us 3/4 j, and we add this pi squared over 8 to the other side. We end up with this. Multiplying by 4/3 on both sides gives you j is equal to pi squared over 6. So There we go. We've just shown that the sum of the reciprocals of the squares is equal to pi squared over 6. Hope you enjoyed that, and we'll see you next time.